Dear friends, a very good morning to all of you, and welcome back to this third and final lecture on manipulator kinematics. In the last two classes, we discussed about the formulation of kinematics problem for industrial robots or the manipulators, and in a systematic way we saw how do we develop the arm matrix or the forward kinematic relationship for a industrial robots. We saw it by systematically assigning coordinate frames and getting the DH parameters, and then developing the homogeneous transformation matrix. We will be able to develop the arm matrix or the arm equation for a robot manipulator. So today we will discuss the next problem of inverse kinematics and the velocity relationships between the Cartesian frame and the joint frame, and look into the issues of singularity and Jacobian and things like that. So as briefly mentioned in the last class, we will be discussing about the inverse kinematics problem, the definition of the problem, and the solvability of a inverse problem. It does not mean that always the inverse can be solved. There are some issues and there are some conditions under which we can solve the inverse kinematics. So we look into the solvability, and then we look into the solution strategies. How do we actually solve the inverse kinematics problem for a given manipulator? And after that we will look into the velocity relationship. We will talk about the Jacobian, then singularities, and briefly touch upon the statics of manipulator, or how do we actually look into the static force analysis of the manipulator, especially the joint torque to get a particular static force applied at the tool tip. So the issue of manipulator inverse is that or the requirement for inverse analysis is that most of the times when we talk about industrial robots, we will be always talking about how do we manipulate a physical object in space. As we know that a manipulator in the forward problem, this Q or the joint variables will be given, and what you are trying to do is to get the tip position or the tool tip position in terms of XYZ. So the position X will be a function of joint variables, and therefore once you know the joint angles, you can always find out the tip reached by the manipulator. So that is basically the forward problem. But in practical applications, the requirement is not that you calculate the tool tip position. The requirement is that this manipulator has to pick up some object from here. Suppose there is an object here, and the position of this object is given as XYZ by XYZ coordinates. So what I was mentioning about the inverse problem and how it is important. You know, in forward kinematics, we will know the joint variables, and once you know the joint variables, we will be able to get the position of this tool tip using the forward relationship. X is a function of joint variables. But in most of the times, what we require is not this relationship. Mostly if you are using a robot, you want to take a workpiece or pick up a workpiece and place it somewhere. So assume that there is a workpiece at this location. The location is given by its coordinates XYZ, and probably the orientation of the object also given to you. We need to find out what should be these joint angles so that this gripper can actually come and pick up this object, so that I can actually bring this gripper here and then pick up this object. So what should be this joint angle so that this can actually come from here and then come to this position and then pick up this object. So that is basically what is needed in most of the inverse problem or most of the practical applications of robots, because I want to pick up this object from a known location and place it at a different location. Now I need to place it somewhere here. So the object needs to be placed somewhere here. So if it has to pick up from here, and then it has to move from here to here and place this object here. So again the gripper should be in this position, and we need to know what should be these joint angles which actually will make this robot to come this side and then place it here, this position. Suppose this position is also known x1, y1, z1, and this one is xyz. We need to find out what should be these joint angles which actually make the robot to come and pick up this object as well as to place this object. So this problem is more interesting in manipulator kinematics, because most of the practical situations we will be facing this inverse problem rather than the forward problem, and that is why it does, most of the time it is formulated in the terms of desired position and orientation. So what is the desired position and orientation is mostly specified in manipulator kinematics. And another problem is that there is no way of to get a systematic closed form solution applicable to robots in general. So there is no way we can actually get a forward kinematics. It was possible to get a general solution for forward equation, but for inverse kinematics there is no general solution for any for robots. For each individual robot, we need to find out what will be the solution for that particular robot. So depending on the robot kinematics, the configuration, the inverse solution varies, the way to solve the problem also changes, and therefore we cannot have a general way of solving the problem. So there is no generalized solution for inverse kinematics. And many times it is not possible to find a unique solution. The solution may be, there may be multiple solutions depending on the type of robot, the type of the position where you want to reach, there may be multiple solutions. So unique solutions are very rare. You cannot find a unique solution for a for inverse problem. And because of all this, it is much more difficult than the forward problem. So inverse problem is much more difficult than the forward problem, because there is no generalized solution, there is no unique solution, and many times you will get multiple solutions also. Now to define this problem, let us look at the way we define the arm matrix. So the arm matrix is defined as the T tool to base is given by this matrix, where you have this position vector PQ here and the rotation matrix RQ here and 0 0 0 1. So this is the way how we get this a relationship, because this is a function of the joint variable Q. If it is only rotary, then it will be theta. If it is prismatic, it will be D. So in general, the generalized variable Q. So this tool to base will be always a function of Q. So the inverse problem is to see if this is given, how do we get this Q? So that is basically inverse problem. In general, we Q, we actually get tool to base relationship. So in general, we will see that the tool to base relationship is always given as Px, Py, Pz as the position of the tool tip, and this normal vector, approach vector and sliding vector as the orientation. Normal sliding and approach vector, NSA. So now if we know this position and orientation of the tool tip to reach, then how to get this Q, the joint variable, is the problem of inverse kinematics. So you can see, the given a desired position P and the orientation of the tool or the tool tip, how to find the values of joint variables Q to satisfy this is basically the inverse kinematics problem. So the inverse kinematics problem is that if this is given to you, if the position and orientation of the tool tip is given to you, or whatever the orientation needed, suppose this is the orientation needed for the tool tip and this is known, if this position and orientation is known, how can I find out the joint angles to reach this position and orientation? And finding out those joint angles is basically, the joint variable is basically the inverse kinematics problem. So the position vector P and the orientation is known, how do you get the joint variable is basically the inverse kinematics problem. So to summarize these two, so what we discussed, we saw that the direct kinematics is the mapping from joint space to tool configuration space. Okay, so joint space Q to configuration space X is the direct kinematics problem, and the inverse is from the configuration space to the joint space is the inverse kinematics problem. Now, how do we solve this one? So if you look at this relationship, you can see that the tool matrix or the arm matrix or the position of the tool tip is given in terms of the matrix P or Px, Py, Pz, and here normal, sliding and approach vector, basically nx, sx, ax, ny, sy, ay, nz, sz, az. And this one, for the forward arm matrix or forward equation, this will be given as a function of join variables. You saw that in the forward kinematic relationship, when we do this T2 to base, you will get a matrix in terms of join variables, like you will get it as C1 multiplied by S1 something plus D1 cos theta. So this is the way you get the relationship for each one. So the inverse kinematics problem is solved by equating this to this and then trying to find out or solve the join variables. So if you look at this Px, you will be having a term here which actually represents Px. There will be a term here which actually represents Py in terms of join variables theta 1, theta 2, theta 3, etc. So now you equate this one to this, equate this one to this one to this. So like this, you will be getting 12 equations from this relationship, because there are 12 variables Px, Py, Pz, and then there are 9 from the rotation part and 3 from the position part. So totally you will be able to get 12 equations from here. So look at this on the slide. So we have this Px is equal to C1 1.77, 177.8 C2 plus etc. For in the previous forward relationship for one of the manipulator, we saw that this is the forward relationship. Now if you apply this, Px is equal to C1 multiplied by 177.8 C2 plus 177.8 etc. You will get one equation. Similarly, Nx is equal to something, then Az is equal to minus C234. So like this we will be able to equate them, and therefore you will see that you can actually get 12 equations from this one. So 12 equations, and you will be having n unknowns depending on the number of joints for the robot. If it is a 6 degrees of freedom robot, you need to find out 6 unknowns. You need to find out theta 1 to theta 6 for a 6 degree of freedom robot to get a desired position and orientation. So we have 12 equations and n unknowns. So depending on the n degrees of freedom robot, you will be having n unknowns. So it seems to be a simple problem. You have 12 equations and n unknowns, and most likely the robot will be having 6 degrees of freedom, so or 6 or 5 or 7 like that. But so it seems to be a simple problem. But one issue with this one is, if you look at this part of this one, this matrix, this actually has got some properties. Okay, so basically if you look at this, ax square plus ay square plus az square is equal to 1, or square root of ax square plus ay square plus az square should be equal to 1. Similarly, this one also it should be equal to 1. This one also should be equal to 1, because this is a vector, approach vector, sliding vector and normal vector. Similarly, n dot s is equal to 0, s dot a is equal to 0, because they are orthogonal vectors. So these 9 equations, though we have 9 equations coming from this, out of these 9 only 3 are independent. Only 3 equations are independent equations, or out of 9 we have only 3 independent equations. All the 6 are dependent because they are all dependent each other. These elements are all dependent each other. So you don't get you don't get 12 equations, but what you are getting is only 3 equations from the rotation part. So from the orientation part you will get, the rotation part you will get 3 equations, and from here you will get another 3 equations. We can actually say, right, Px is equal to this one, Py is equal to this one, Pz is equal to this one, you will write. So you will get another 3 equations. So totally you will be getting 6 independent equations from the arm matrix. So we have 6 independent equations which can be used to solve the unknowns here. You have 6 independent equations and you have n unknowns. So as long as this 6 is, it's a 6 degrees of freedom, you can solve, because you have 6 independent equations and 6 unknowns, you will be able to solve. If it is 7, you won't be able to get a unique solution, you will be always getting multiple solutions, because one of the angles need to be assumed and you will be able to, you need to solve it separately. If it is 5, again you will be able to solve the equation, because you have n unknowns and 6 independent equations and n unknowns. So that is the solvability of the equations, or the inverse problem. The first issue with the inverse problem, we start from the forward kinematic relationship and then try to write down the equations representing the as a function of join variable, and equate them to the given Px, Py, Pz. Assume that this is given to you because we need to find out the joint variables corresponding to this one. So we will write Px is given as 800, we will write 800 is equal to this and 700 is equal to this, like that we will be writing and then trying to solve for the joint variables. But apart from this, these equations are non-linear, they are not linear equations because they are functions of theta, theta 1 plus theta 2 etc. and they are non-linear equations and not so easy to solve. We need to have some special methods or some ways to solve these equations depending on the type of equation that we are arriving at. And apart from this, we need to look at whether the solution will be there at all or not. So that is basically so first we look at the solvability, then we look at the solvability. Basically tells that you have 6 equations and you can n degrees of freedom, so you will be able to use this one to solve it. The next one is the existence of solution, whether the manipulator is solvable or not. It's not that every manipulator you will be able to get an inverse solution, not possible, or it may not be there, the solution may not exist at all. So how do we look at the manipulator and then see whether the robot can be solved or not, whether the inverse solution can be found out or not. So a manipulator is solvable if all the sets of joint variables can be found corresponding to a given end effector location. If an end effector location is given to you, if this location is given to you, if we can find out all the joint angles corresponding to this location, then we call it as, then we say it is solvable. That means the manipulator is a solvable one. And there are some conditions under which we can ensure this. So these are, first one is the necessary condition to have a solution. The necessary conditions to have a solution. Okay, there are two, one is necessary condition, the other one is sufficient condition to get a closed form solution. So first we look at the necessary condition. The necessary condition, the first condition is that whatever the joint, the tool position that you are suggesting or you are trying to solve should be within the workspace of this manipulator. You should not specify something outside the manipulator and tell the inverse problem to solve this one. Okay, so first condition is that the point should be always within the workspace. Anything which beyond the workspace of the manipulator cannot be solved, or there will not be any solution at all for that kind of a problem. So that is the first condition. And the second condition is that if the number of degrees of freedom is equal to 6 or more than 6, then only all the orientations can be found out. I mean, if you have n is equal to 6 or n is more than 6, that means you will be able to get any orientation at the tooltip. If n is less than 6, then you won't be able to get all the orientations. So some orientations will be depending on other orientations. So if n is equal to 5, you will be able to get only 2 orientations independently. The third one will be a function of the first 2. So that way, if n is 6 or more, then only you can suggest any orientation, arbitrary orientation. Otherwise, you need to suggest only normal or sliding or approach only you can suggest, and the third one will be depending on these 2 you will be able to get. If you want to suggest all these 3, normal, sliding and approach vector and the position arbitrarily, then it should have minimum 6 degrees of freedom, otherwise you won't be able to solve it. So these are the necessary conditions, and of course the tool orientation is such that none of the joint limitations are violated. Again, you will be having these limitations for the joints. This joint won't be able to move to 180 degree from this position to this position. And if you suggest a position or a tool position where the joint angle needs to travel 180 degree, then the robot will not be able to get a solution for that because the joint limit will be violated. So that also should be taken into account when we consider the inverse solution. So to have the necessary condition to have a solution is basically the point should be within the workspace, and any arbitrary orientation if you want, then n should be greater than 6 or equal to 6, and the joint limit should not be violated. So these are the necessary conditions to have an inverse solution. And solution can be of 2 types. One is known as a closed form solution. Closed form solution. The other one is the analytic numerical solution. These are the 2 ways in which actually you can do the inverse solution. And closed form solution is basically the one which actually you solve analytically using these equations. So you have 6 equations independent equations, you will solve them analytically and get a solution that is basically known as closed form solution. And the numerical solution is that you using an iterative algorithm, you start with an arbitrary any joint angle and try to find out all other possible joint angles to get a particular position. Numerically you solve it. That is basically the numerical solution. So numerical solution is actually time consuming, and most of the times you will be able to get a closed form solution easily, and if the closed form solution is not possible, then you need to go for a numerical solution. So closed form solution is using the trigonometric relationship and the algebraic equation what we saw, you use those equations and solve, that is known as closed form solution. And when the closed form solution is not possible, we will go for a numerical solution. By iterative search, you try to find out a solution which actually satisfy all the conditions given in the relationship or the inverse relationship. And to have a closed form solution, in order to have a closed form solution for a manipulator, that is the necessary sufficiency condition to have closed form solution. So by looking at the manipulator configuration, we will be able to tell whether you can really find a closed form solution or not. And in some cases you won't be able to get a closed form solution, then you have to go only for a numerical solution. So the sufficiency condition for closed form solution is basically, the first one is three adjacent joint axes intersecting. So one condition is that the three adjacent joint axes are intersecting. So Z4, Z5 and Z6 are intersecting at one point. The joint axis, three adjacent joint axes 4, 5, 6 or 1, 2, 3, whatever it is. If they are intersecting, then you can always be assured of a closed form solution. Or three adjacent axes are parallel. If you have joint here and the joint here and the joint here like this, and Z1, Z2, Z3 or Z3, Z4, Z5, whatever it is, if three joint axes are parallel, then also you can be assured of a inverse solution, a closed form solution for the manipulator. So these are the two conditions under which you can be assured of a closed form solution. If it is not there, then it's very difficult to solve the equations algebraically, or in an analytical way you won't be able to solve these equations, and therefore you may have to go to numerical methods only. So these are the conditions for getting the closed form solution. And another important characteristic is about the uniqueness of solution. As I told you, it is not necessary that you will be always getting a unique solution. There may be multiple solutions most of the times. If the number of degrees of freedom is more, then you will be always getting a multiple solution, because if you have 7 degrees of freedom and you have only 6 independent equations, so you won't be able to get the 7th joint solved. So you need to assume one joint angle for one of the joints and then solve for the next 6. So depending on the first joint angle you assume, you will be able to get multiple solutions. That is, for redundant robots you will be always getting multiple solutions. And another case of multiple solution is known as elbow up and elbow down solutions. Suppose there is a robot here. So this robot is like this, and it actually has to reach to this position here. The robot has to reach this position. So it can actually go from here, or it can actually go from here also. So you can actually have a position like this also. So this is one solution to reach here, and this is another solution to reach here. So this is known as elbow up and elbow down solutions. Again, you will be having multiple solutions in this situation also. So these are the cases where you will find that uniqueness of solution is not there. You can always get multiple solutions. So this also need to be taken into account when we are trying to solve the inverse relationship. Okay, so let us try to see how to solve a problem like this. So in closed form solution, as I told you, you can go for an algebraic approach or a geometric approach also. So closed form solution is that you solve the equations, in an analytical way. That is basically the closed form solution. And here you can go for an algebraic approach or a geometric approach. Geometric is basically you look at the possible ways in which actually you can reach this position in a in a graphical way. You try to see, you know the length of each link. So you try to plot this link in different positions and then see whether we can actually reach this position, and then see what should be the way in which actually it has to be arranged to get this. That is basically the geometric approach. Sorry, geometric approach. Algebraic is basically you solve this equations in an algebraic using algebraic methods. These are the two ways in which the closed form solutions can be approached. We will be doing only the algebraic approach here, because geometric approach is again looking at the geometric features of the links and then trying to solve it. So we will see the algebraic approach and how this can be solved. So we use a few tricks to solve this. When I said tricks, basically some methods to solve the equations. The first one is basically use trigonometric identities to combine two equations, such as first square them and then add them and eliminate certain variables. So if you have like cos theta 1 cos theta 1 plus sin theta 2 and sin theta 1 plus cos theta 2, you add them, some of them will get added up, and you can see cos square theta plus sin square theta is equal to 1, and therefore that will get eliminated. So like that you will be able to do some trigonometric identities. Using trigonometric identities you can reduce the complexity of the equation and try to solve it. The second one is use the variable substitution. Okay, sometimes you substitute some variables and then convert that equation into a different form of equation. For example, you substitute u is equal to tan theta by 2, then cos theta becomes 1 minus u square by 1 plus u square, and sin theta becomes 2u by 1 plus u square, and you will be able to use this one to solve the equation. So that is another method of converting the equations to polynomial ones. So you convert these trigonometric equations to polynomial equations and solve the polynomial to get the joint angles. The third one is find out expressions of both sine and cos of a joint angle and express the angle using the function a tan 2. A tan 2 is a function or arctan. So basically arctan sine theta cos theta. So you find out some expression for sine theta, some for cos theta, then theta will be a tan sine theta cos theta. We don't directly take the sine inverse to get the theta, and there are some reasons, I will explain it later, but this is one way to get the joint angles. You express in terms of sine theta and cos theta and then use a tan 2 function. So there is something called a tan 2 function in MATLAB, and in Mathematica a tan itself gives you the function. Basically it will tell you in which quadrant the angle lies, because if you simply take a tan, arctan, it could be either here or here. So we don't know where it actually lies. So but a tan 2 function, by looking at the sign of these two arguments here, you will try to find out in which quadrant the solution lies. That is basically a tan 2. I explained this when we take a case study, but that is another method of finding out the joint angles using trigonometric using some substitutions and getting the theta from arctan functions. Okay, let us take a simple example first, and then we go to a complex example, slightly complex example also. So consider this as a planar manipulator, a 3 degree of freedom planar manipulator with okay, only planar, so it is actually basically one, then another one, and then another one at the tip. So 3 joint angles. And you can see these are the coordinate frames assigned. So you have 3, all the joint axes are vertical, so it actually rotates, and then this is what actually the tool to base is given. So it is given that you need to reach a particular position px, py and pz, and this is the orientation vectors to be achieved. So it is n, s, n, a, so nx, sx, ax, etc. So for this manipulator, we need to solve for this theta 1 to theta 1, theta 2 and theta 3, which will actually take this to a particular px. So if I am specifying a px, py, pz, I want to know what should be the joint angles corresponding to this for this manipulator. So for any given values of px, py, I should be able to get theta 1. So I need to get a relationship theta 1 as a function of these parameters. So theta 1 should be solved, theta 2 should be solved, theta 3 should be solved as a function of these parameters. So what I know is only this. So using this I need to solve this for this theta 1, theta 2, theta 3. So first thing is to get the inverse solution is you need to have a forward solution, because we need to know what is the forward relationship for this. So how Px can be written as a function of theta 1, theta 2, theta 3, and I need to know. So that is the first thing to be there. So first I will start with the forward solution and try to find out a forward solution, which is given as Px is equal to L1 C1 plus L2 C12. L2 C12 is Px, and Py is L1 S1 plus L2 S12. S12 means sin theta 1 plus theta 2. So that is basically the forward relationship. So similarly, I can write all these one. See, Nx is equal to C123 cos theta 1 plus theta 2 plus theta 3 is Nx. Ny is equal to S123. So these are the equations. So from here I will be able to get 12 equations. 3 from Px, Py. Okay, in this case Pz is equal to 0. Sorry, Pz is equal to D1, and Nx, Nz and Sz will be 0. Az will be 1, and Sx, Xy are given like this: C123, S123 minus S123, C123. So you will be getting 12 equations. Out of this 9 are 6 are independent. So we will be able to write it as Nx is equal to C123, Ny is equal to S123, Sx is equal to minus S123, Sy is equal to C123, and Px is equal to L1 C1 plus L2 C12, Py is L1 S1 plus L2 S12. So these are the equations which can be used for solving the relationship. So now it is the job of the designer or the person who actually tried to solve it to find how can we solve this equation, because solving the equation is not straightforward. You need to find out how to solve it. So we need to get theta 1, theta 2 and theta 3. We need to solve it. We need to solve theta 1, theta 2 and theta 3. So the first step is to look at this equation, then see can we do some tricks to solve it. So we talked about 3 tricks or 3 methods to solve it. So now I can see that equation 5 and 6, if I square and add 5 and 6 to get Px and Py, if I write Px square plus Py square, I need to find out what will be the relationship. So I can actually square and add this 5 and 6. We get it as Px square plus Py square is equal to L1 square plus L2 square plus 2 L1 L2 C2. So I can write it as L1 square plus L2 square plus 2 L1 L2 C2. You can see how it comes. So I will add this L1 square C1 square plus L2 square C12 square plus 2 L1 L2 C12. Similarly, I will be squaring this and adding, and this was C1 square plus S1 square will become 1. So L1 into C1 square plus S1 square plus L2 into L2 square into C1 square plus square. And if you do this, you will be able to get this as Px square L1 square plus L2 square plus 2 L1 L2 C2. Now C2 can be obtained from here, because cos theta 2 can be obtained from here as Px square plus Py square minus L1 square plus L2 square divided by 2 L1 L2. So you will be able to get it as Px square plus Py square minus L1 square plus L2 square divided by 2 L1 L2 will be C2. So we have an expression for C2 with all the known parameters, because we know L1, we know L2, all these things are known, we know Px and Py, and therefore we can find out what is C2. So cos theta 2 can be obtained. Now we don't use this cos theta 2 directly to get theta 2, because that actually will lead to some other problem. So what we do, from C2 we will try to find out what is S2, sin theta 2. We know that C2 square plus S2 square is equal to 1. So sin 2 will be calculated as plus or minus square root of 1 minus C2 square. So this will be plus or minus 1 minus C2 square will be given as, taken as S2. So we got C2 and S2. Now we use this a tan 2 function. A tan 2 S2 C2 will be theta 2. And of course we have 2 values for sin theta 2. So therefore we will be able to get 2 theta 2, and then depending on the joint angle limitations you have to choose one of the joint values for theta 2. So that is the way how you get the theta 2 for this one. So first one we will solve for theta 2. So why a tan 2 function is, a tan 2 actually represents the 4 quadrant version of arctan function. So a tan 2 is a 4 quadrant version of arctan 2. Depending on this sign of S2 and C2, it will decide in which quadrant the angle lies. So if S2 and C2 are 0, then the result is indefinite. X is greater than 0 and y is equal to 0. So if it is positive and 0, similarly negative and 0, under different conditions you can see the a tan 2 function will be pi, or it will be between 0 and minus pi and between 0 and pi. So you will be able to get it where the actual function lies or actual angle lies, whether it is on this or in this 0 to pi, or it is in this quadrant it is lies, you will be able to get it. So that is basically the a tan 2 function. So we use this a tan 2 function to get the solution for theta 2. So that is the first step, theta 2 obtained. We need to get theta 1 and theta 3 to be identified. Now if you look at, for theta 1, we can actually use for theta 1 is px is equal to k1 c1 minus k. This is actually a substitution, slightly complex way of do this. So we substitute k1 px, we write it as k1 c1 minus k2 s1 and py as k1 s1 plus k2 c1, where k1 is l1 plus l2 c2 and k2 is l2 c2. So we do some substitution to solve this problem. So that actually depends on the type of problem. Some cases you don't need to do this method, some cases you need to do this. So that depends on the manipulator. That's why there is no general way of doing it. You have to look at the equation and then try to solve it. So here we do a substitution, k1 is equal to l1 plus l2 c2 and k2 is equal to l2 s2, because now theta 2 is known, therefore k1 can be obtained as l1 plus l2 c2, l2 and c2 are known, you will get k1. Similarly k2 also you can get. So you will see that you substitute for k1 and k2, you will get, you will be write px as k1 c1 minus k2 s1 and py as k1 s1 plus k2 c1. Now again you substitute k1 is equal to r cos phi, cos gamma, k1 is equal to minus r sin gamma, where r is k1 square plus k2 square and gamma is a tan 2 k2 k1. Because k2 and k1 are known, you will be able to substitute this and then get the equation as px by r is equal to cos gamma cos theta 1 minus sin gamma sin theta 1. Py by r is equal to cos gamma sin theta 1 plus sin gamma cos theta 1. So by substituting this, you will be able to get this relationship, and that will give you cos gamma plus theta 1 is equal to px by r and sin gamma plus theta 1 is equal to py by r. So here gamma is known and px is known, py is known, r is known. Therefore you will be able to get theta 1, cos theta 1 and sin theta 1, and you will be able to solve it as theta 1 is equal to a tan 2 py px minus a tan 2 k2 k1. So this is the way how theta 1 can be solved by substituting. So we actually do the substitution here. We substitute for k1 k2 and define gamma and simplify the equation 5 and 6 and bring that into a form where cos gamma plus theta 1 is equal to px by r and sin gamma plus theta 1 is equal to py by r, and write gamma plus theta 1 is equal to a tan 2 py by r px by r is equal to a tan 2 py px. Theta 1 is a tan 2 py px minus a tan 2 k2 k1. So since k2 k1 is known, py px is known, you will be able to get theta 1. So theta 1 can be solved by that relationship. So theta 1 is known now and theta 2 is also known, and we need to get theta 3. So to get theta 3, we will find out what is theta 1, 2, 3. Theta 1, 2, 3 can be obtained from the equations 1 and 2, that we had this nx and sx relationship, nx, ny and sx, sy relationship. From 1 and 2 we get theta 1, 2, 3 is a tan 2 ny nx, because we can write, we know ny and nx. So a tan 2 ny nx will give you theta 1, 2, 3, because nx is equal to cos theta 1, 2, 3, cos theta 1, 2, 3 and ny is equal to sin theta 1, 2, 3. So a tan 2 ny nx will give you theta 1, 2, 3. So once theta 1, 2, 3 is known, we can get theta 3 as theta 1, 2, 3 minus theta 1 plus theta 2, we will be getting theta 3. So theta 3 is theta 1, 2, 3 minus theta 1 plus theta 2, you will be getting theta 3 also. So again theta 3 you will be getting the relationship. So for any value of this you will be able to get theta 1, theta 2 and theta 3, and that is the inverse solution for this particular manipulator. So you can see that we start with the forward relationship and try to write down the equations, the 12 equations, and then solve those 12 equations in an algebraic way using algebraic relationships and the tricks for solving them by substitution or by squaring and adding, and try to get a relationship to solve this theta 1, theta 2 and theta 3. So this is the way how we solve the inverse kinematics problem for manipulators. So the challenge here is to bring these equations into a form which can actually be easily solved or which are non-trigonometric identities. So there are some non-ways of solving the problem. So if you can bring those equations, the 12 equations into some non-methods, you will be able to get the solution. So some of the commonly used solutions are, if you have an equation like A is equal to B sin theta, then theta can be solved by this relationship. So if you can bring all the equations into any one of these forms, it can be solved easily. You don't need to go to the substitution which I already mentioned. That was just to show you how the substitution works. But in the practical situation, you don't need to really do it. What you need to do is to bring these equations into a standard format. For example, if you can have an equation like A is equal to B sin theta, then theta can be solved using the relationship shown here. It is A tan 2 A by B square root of 1 minus A by B square. So this is the way how you do the solution. So once you can bring this equation to this format, you can get directly the theta. The other one is, okay, A is equal to B cos theta, also same way you can solve. The other one is, if you have something like A is equal to B cos theta, A is equal to B cos theta, and C is equal to D sin theta. Suppose you have an equation, you have the two equations like this, you will see that this kind of situation arise very often. In another example I will show you. So if you can bring into this format, then you can get theta as A tan 2 minus B, A tan 2 C by D A by B. So theta will be A tan 2 C by D A by B. Okay, another one is A sin theta plus B cos theta is equal to 0. If you have an equation like A sin theta plus B cos theta equal to 0, then theta will be A tan 2 minus B by A. Okay, again these are all the commonly used equations. You don't need to remember all those things, but if you have a chart of this equation, always you can bring your 12 equations into any one of this format and easily solve for theta. Another one is A sin theta plus B cos theta equal to C, then theta will be A tan 2 A by B, AB plus A tan 2 plus or minus square root of A square plus B square minus C square comma C. Another one, A cos theta I plus B cos theta j equal to C. So this kind of format you always see A cos theta 1 plus B cos theta 2 equal to C. A sin theta 1 plus B sin theta 2 is equal to D. If that is the equation, then theta will be A tan 2 D C plus A tan 2 plus or minus C square plus D square minus S square comma S, where S is equal to A square minus B square plus C square plus D square over 2A. Okay, you don't need to note down all these things or remember all this. Okay, assuming that this is known to you or this is given to you, you will be able to convert your equations into the standard formats. Because for any manipulator, you have to do an inverse only for the one time. Okay, you don't need to do it every time. One time you have to solve the inverse kinematics of a given manipulator. That holds good for always. Okay, another one is A sin theta plus B cos theta is equal to C. A cos theta minus B sin theta is equal to D. Then the solution will be again A tan 2 AC minus BD plus BD comma AD plus BC, and A square plus B square is equal to C square plus D square. Another one, A cos theta I plus cos theta j, that is cos theta 1 plus theta 2 plus B cos theta 1 is equal to C. A sin theta 1 plus theta 2 plus B sin theta 1 is equal to D. Again you can have a solution. So if you can bring this into any of these standard formats what I have shown, then solution can be easily obtained. You don't need to go for the substitution what we discussed in the previous example, because it actually comes from those substitutions. So the solution method is solution is already given, so you can use simply these to solve the inverse equations. Okay, another one is Px is equal to, okay, this is an example what I have given. Px is equal to L1 C1 plus L2 C12, Py is equal to L1 S1 plus L2 S12. The previous case what we discussed, it was this case condition, Px is equal to L1 C1 plus L2 C12, Py is equal to L1 CS1 plus S2 S12, C2 is Px square plus Py square minus L1 square plus L2 square by 2L1 L2. That is what actually we are used in this equation here. Okay, this is just to tell you that there are ways to solve the problem. So the only thing what you need to do is to bring it to a standard model, standard equation. So with this, let us take just one more example and show you how to solve the kinematics of a general or a 5-axis articulated arm. So what we discussed was a simple one, 3 degree of freedom previously, planar manipulator. Here it is a spatial manipulator with 5 degrees of freedom, and we saw this in one of the classes, earlier classes. I gave it as an exercise for you to find out the DH parameters. So what we need to do is to get the solution for theta 1 to theta 5. We need to solve for theta 1 to theta 5 in terms of Px, Py, Pz, and of course N, S, N, A. So assume that this is given to you. You need to find out what is theta 1 to theta 5 for any values of these parameters. Okay, and only in this case it's a 5 degree of freedom. So you cannot really get all the orientations. So only 2 orientation will be independent, and one will be dependent on the other. Okay, so when you get a manipulator, first thing you have to do is DH parameters and then the forward relationship, and from the forward relationship you write down the equations. Okay, so I am just writing the few equations what we get from the forward relationship. So you can write Px is equal to, if you go back to your old last lecture slides, you will see that we solved it for forward kinematics, and they can see that Px is given as cos theta 1 multiplied by A2 C2 plus A3 C23 plus A4 C234 minus D5 S234, and Py is again S1 multiplied by the same parameters, and Pz is D1 minus A2 S2 minus A3 S23 minus A4 S234 minus D5 C234, and Nx is given, Ny is given, Ax is given, Ay is given. So we have many equations. So we have you can have 12 equations like this, and these 12 equations to be solved to get expression for theta 1 to theta 5 in terms of all these position and orientation, required position and orientation. So let us see how to solve this. So take the first equation Px and Py. So we can see that Px and Py, C1 and S1 are there, and the term within the bracket is the same. Okay, you can see within the bracket it is A2 C2 plus A3 C23. We can easily see that can be used to solve for theta 1. So theta 1 can be easily solved using that relationship. So please try to solve theta 1. How do you get theta 1 from that? So what will be Px over Py or Py over Px? Okay, Px over Py is C1 S1, and theta 1 is A tan 2 Py Px. Okay, so A tan 2 Py Px will give you theta 1. Simply take theta 1 as, theta 1 will be obtained as A tan 2 Py Px. Since Py and Px are known, you can easily get theta 1. Now if you go back to the previous diagram, you can see that this theta 1 is the vertical axis. So if this is in the plane, anything going out of the plane is the theta 1. Okay, this is theta 2 in this direction. So theta 1 is anything out of the plane, and it is very clear that the Py, the y coordinate is always decided by this theta 1, because it is going out. Y coordinate, this is xz plane, so y coordinate is always decided by theta 1, and you can easily find out the theta 1 if you know the y coordinate and x coordinate to be reached. You will be able to get theta 1. So the first joint angle can be easily solved for this. So you got theta 1. The next one is to look for other joint angles. So we will take the equation Ax is equal to minus C1 S234, Ay is equal to minus S1 S234, and S234 can be written as, from this one you can write Ax C1 plus Ay C1. So S234 is equal to minus Ax C1 plus Ay C1, and C234 is minus Az. So these are all the this C234 is equal to Az is already there, and using the first Ax and Ay, we can write Ax C1 plus Ay S1 is equal to S234, and C234 is already there as minus Az, because C1 is known. Now C1 we already know, because theta 1 we already found out. We know what is cos theta 1. We can substitute here and we will get S234 as some value and C234 as another value. These are both are known. Ax is known, Ay is known, C1 is known, S1 is known, Az is known. Therefore, we have S234 and C234. We can get theta 234 as a tan 2 of this. A tan 2 of this will give you theta 234. So we have solved theta 1 and we have solved theta 234. Theta 234 is also now solved using this relationship. And you can always see that whenever there is whenever there are the axes, three axes are parallel or intersecting, you will always see that this kind of an equation arrives, 2 plus 3 plus 4 or 1 plus 2 plus 3, and that is when you can have a solution. If it is not coming like this, very difficult to solve, and that is why when we are saying that to get a closed form solution, the sufficiency condition is that three axes are parallel or intersecting. So here, because they are parallel, you can see that these angles are adding up here like this. Okay, now we go to the solution of theta phi now. Because again from nx and ny, you look at the equation, nx is equal to something and ny is equal to something. Similarly, sx is equal to something, ny is equal to sy is equal to something. We can write sy is equal to nx s1 minus ny c1. So we can write s5 as nx s1 minus ny c1. You multiply nx with c1 and ny with s1, and you subtract, you will get s5. Similarly, cos phi can be obtained. Cos phi is sx s1 minus sy c1. So because s1 is known, you will be able to get s phi and c phi. Again, theta phi will be a tan 2 s5 c phi. So theta phi also solved. So we have solved theta 1, theta phi and 2, 3, 4. What we need to do is to solve 2, 3 and 4 separately. We need to get value of theta 2, 3, 4 in terms of 2, 3 and 4 in terms of the known values. Okay, so to do that, we take the Px and Py equation, that is equation 1, and write it as A3C23 plus A2C2 is equal to, so the equation 1, if you go back, the equation 1 is this one, Px is equal to C1 A2C2 plus A3C23 plus A4C234 minus D5 S234. So in this equation, now if you look at this Px equal to that equation, you know that theta 1 is known and theta 5 is known, theta 2, 3, 4 is known, because we have solved for theta 1, 5 and 2, 3, 4, and therefore we can use these values in this equation Px and write it. We can actually take out the unknown terms A2C2 and A3C23, A2C2 plus A3C23 is known, not known, all other terms are known, because we know 2, 3, 4, we know theta 5 and theta 1, and therefore we can write it as A2C2 plus A3C23 is equal to Px minus the other terms. So that is what we are doing here in this step. A3C23 plus A2C2, A3C23 plus A2C2 is equal to Px by C1 plus D5 S234 minus A4 C234. And similarly, we will write A3 S23 plus A2 S2 equal to D1 minus A4 S234 minus D5 C234 minus Pz. So by changing the first and third equation, by substituting the values non-parameters theta 1, theta 5 and theta 2, 3, 4, you will be getting one equation here, and here you will be getting A2 S2 plus A3 S23 equal to something. Now this can actually be calculated because all are known values. This one we will be able to calculate and write it as a numerical value here. So A2 C2 plus A3 C23 is equal to some K1, and A2 S2 plus A3 S23 is equal to K2. Now we know K1 and K2. what we need to do is to solve for theta 2 and theta 3 from this equation. And if you look at, this is actually a standard format of an equation what we discussed in the previous slide, A2 C2 plus A3 C2 plus 3, A2 S2 plus A3 S2 plus 2 plus 3 equal to this parameters. So that's the standard format what we discussed in the previous case, that is A cos theta I plus theta j plus B cos theta I is equal to C, and A sin theta I plus j plus B sin theta is equal to D, and the solution is already given as sin theta and cos theta. So theta j is A tan 2 sin theta j cos theta j, and the theta I is A tan 2 RD minus SC RC plus SD. So simply apply that rule here, the equation, the rule given as theta I and j, use that rule and then find out theta 1 and theta 2. This is what we need to do, because it's a standard format, this one is a standard relationship. So using this equation, you can actually solve for the solution methodology is already there. Simply substitute that, you will be getting it as cos theta phi is equal to c square plus d square minus a3 square minus a2 square over 2 a3 a2, and sin theta 3 is square root of 1 cos square theta 3. So theta 3, cos theta 3 and sin theta 3 is obtained. Therefore, you can substitute for, you can get theta 3 as a tan 2 sin theta 3 cos theta 3. So theta 2 will be, theta 3 can be obtained that way, and theta 2 is a tan 2 RD minus SC RC plus SD, where R is A3 cos theta 3. Now cos theta 3 we already solved, we will be getting R and S can be obtained, and we will be able to get theta 2 also. So we will be able to solve theta 2 and theta 3 using these two equations, using standard formulations, and we will be getting this theta 2 and theta 3. And we know theta 2, 3, 4. So theta 4 can be obtained as 2, 3, 4 minus theta 2 plus theta 3, you will be getting theta 4 also. So this way we are actually solving theta 1, theta 5, theta 2, 3, 4, theta 2, theta 3 and theta 4 independently. So we are getting all the solutions for the joint angles. That is what actually we do in the inverse kinematic. Okay, it may appear to be slightly complex for you, because solving the equations are the challenge in inverse kinematics. So what we need to do is to look at the equations, the 12 equations, and try to find the similarity or the possibility of using the trick to solve it, and whatever the possible ways of solving the problem you need to find out, and then solve it using the standard trigonometric relationship and get the relation for theta 1 to theta n depending on the number of degrees of freedom. So that is the way each problem to be approached, because there is no general solution. The problem is to be approached as an independent case. For each manipulator you have to find out what is the forward relationship and how these forward equations can be solved, provided they actually satisfy the given conditions of necessary and sufficiency condition for solutions. Okay, so this is an exercise for you. You can actually try to get an inverse solution for this problem. We already discussed about these robots, a 4-axis Cara. We have talked about its DH parameters and forward kinematics. Please write down the forward kinematic relationship and try to solve the inverse using the methods I already explained to you. So we discussed about forward and inverse kinematics. We discussed about coordinate transformations. I'll take a simple example of where it is used and how it is used in a practical scenario of a robotic work cell used for some pick and place operations. So look at the diagram shown in the slide, where a manipulator is used for picking and placing an object which is there on the workspace to a pass or reject bin. So the workpiece will come to its the robot's workspace, and there is a camera on top of the workspace which will look at the object and decide whether the object is good or bad. So if it is a good one or it is an acceptable one, it will the robot will be asked to pick up the part from the workspace and put it into the pass bin, and if it is not good, the robot will actually pick up and so this information about the position of the workpiece and its orientation, and the information whether the workpiece is good or bad, both will come from the camera. So under this situation, how the forward and inverse kinematics is applied to help the robot to place or pick up the workpiece and place it in the pass or reject bin is explained I am going to explain the methodology used here. So the first thing is to know where the part is. With respect to some robot, some coordinate frame, the position of the part is to be identified. So the position of the part is given with respect to camera. So the camera is looking at the object and then try to find out the position and orientation of the workpiece with respect to camera, and that is given as T part to camera transformation. Part to camera is given by the camera, that what is the position of this part with respect to the camera is obtained from the camera images, and the position Px, Py, Pz and the orientation will be obtained. So that is what part to camera, the position and orientation of the workpiece is given. So the part is -5, that is 5 mm away from the y in the y axis, 19 mm below the z axis. So it is around 9 below and 5 away from the y, that is given as 0, -5, 19, and its orientation is also given. Now the robot needs to know what is the position of this workpiece with respect to the robot coordinate frame, because if the robot has to go and pick this up, it should know what is the position of this one, and for that we need to know the transformation part to robot base. This is to be known, T part to base to be known. Unfortunately the robot won't be able to get it directly, so it has to use this information and find out what is the position of the camera with respect to the robot base. So the another transformation is camera with respect to base should be known, okay, or the base to camera, any one of these. So base to camera is given, what is the transformation from robot base to camera is known, because camera is fixed here, so we need to know what is the transformation from here to here, and here to here is already given, and therefore you will be able to find out what is the position of the part with respect to the robot base can be obtained by these two transformations. That is the first one. So we try to find out the part to base, the position of the robot, the part workpiece to the base of the robot can be found out using these two transformations, part to camera to base and part to camera. So you take that camera to base and part to camera. If you know this, we will be able to get T part to base can be obtained. So we can use these transformations to get the position and orientation of the part with respect to the robot base. That is what we are doing. So you take the inverse of this and then multiply with this, you will be getting the robot position, the position of the part with respect to base. You will be able to get this one. So once you know, once the robot knows that the position and orientation of the workpiece with respect to the base, then it has to find out the joint angles theta to reach this workpiece. So it has to go and pick up this workpiece, and we know the orientation of this one is again a 4 by 4 matrix, where the position of the part Px, Py, Pz and its orientation will be obtained. The position of the workpiece with respect to the robot base will be obtained. Now it will do the inverse kinematics to find out the joint angle to reach this position. So forward kinematics will be used to get the position of the robots, position of the workpiece through the transformation matrix will be used to get the position, and then we will be using the inverse kinematics to solve for the joint angles to pick up this workpiece. So you can see the location of the part with respect to the robot base can be obtained as 30, 15 and 1. Basically it says that x 30 mm 30 units away in the x direction, 50 units away in the y direction, and in the same plane as the z plane of the z axis, it is with respect to robot base, the 30, 15 and 1 is the position of the workpiece, x, y and z. Z is in the same plane, that is why you can see z is 1, because the z plane of in xy plane it is 30, 15 and z plane it is same, z axis. So what we know that part with respect to the base. The next one is basically object grasping by the robot tool gripper orientation. So we need to move this gripper, the robot gripper, to go to this position to take this and grip this object. So we know the position and orientation. So we need to find out the joint angles to go and grip this, and that is obtained through the inverse kinematics relationship. Okay. So based to basis is on the orientation is given, and you solve the inverse kinematics. If the robot is known, if this XR3 Rhino robots, then we know how to solve the inverse kinematics. So you will be able to solve the inverse kinematics by the previous method what we discussed. You will be getting theta 1, theta 2, etc. So theta 1 to theta 5 can be solved, and the robot can be actually moved to grab the object, and again it will do a inverse kinematics to see where to go to the bin, accept bin or reject bin also will be carried out. So that is the way how a real robot works cell inverse kinematics. So whenever we use a robot for a particular application, we need to find out the transformation matrices between various elements in the cell, and then use the inverse kinematics and forward kinematics to solve the problem or to use it for a particular application. This is just to tell you that these are necessary things to know, or when you want to apply a robot for any particular application, these are minimum requirements that one should know. Okay, so that's all about the forward and inverse kinematics. We will briefly go through the differential motion and statics it's applied to manipulators. Okay, so far what we discussed was only the position relationship. So we discussed that x, y, z position and theta 1, theta 2, theta 3 we discussed. So what we are going to discuss is how the velocities can be related. So we know the position can be related through forward and inverse kinematics. So theta can be related to x, and x can be related to theta through forward and inverse kinematics. You have a forward kinematic relationship, all the theta can be converted to x domain, and if you have inverse kinematics, x can be converted to the theta domain. I mean, if you know x, you can find out theta using IK inverse kinematics. If you know theta, you can get theta x using forward kinematics. What we are trying to do is, can we get a relationship between theta dot and x dot? Similarly, x dot is given theta dot, whether we can do this, because I want to have my robots move with a particular velocity. I am not interested in position. I want this robot to move from this position to this position along this path with a particular velocity. I am interested in getting a x dot, y dot velocity and z dot for the velocity of this motion. So if I want to move this with a particular velocity x dot, y dot, z dot, I want to know what should be the velocity, joint angle velocities to be commanded, because velocity, Cartesian velocity x dot, y dot, z dot will be always depending on the joint angle velocity. So I am interested in finding out a relationship between the joint angle velocity and the Cartesian space velocity. So what I have been talking about is the differential relationship. What we need to, so far we discussed about the position relationship, position and orientation, but in the real scenario what we require is more of a velocity relationship, because we want to command a manipulator with a particular velocity in a workspace. We need to know what should be the joint angle velocities to be commanded to get the desired Cartesian space velocity. So that is basically obtained from the forward relationship, because forward relationship basically tells about x is a function of q. So let's just put it as xwq, and which is the x is the tool configuration or the Cartesian space, and q is the joint space. Now if you want to get a differential relationship, what we need to know is to x dot, how x dot is related to q dot. So this is what we need to find out in getting the relationship. So whenever whenever there is a change in q dot, what will be the variation x dot, or whenever I want to get a particular x dot, what should be the q dot. So this is basically known as the velocity relationship. So the tip velocity and Cartesian velocity relationship is known as the that is basically the differential relationship, and this is given by x dot is equal to j q dots, where j is known as the Jacobian of the manipulator or Jacobian. So x dot is the Cartesian velocity, q dot is the joint angle velocity, Cartesian or the tool velocity, and the joint angle velocity. They are related through a matrix called Jacobian, which is j, and this is obtained by taking the derivative of w, the forward relationship, with respect to the joint variable. So the elements of j is obtained as partial derivative of w with respect to q. That is, the forward relationship with respect to the joint angle, you take the partial derivative of this relation with respect to joint angle, you will be getting the elements of J, and which is known as the Jacobian of the manipulator or the Jacobian matrix. So J is partial derivative of W with respect to Q, where K is 1 to 6 in this case, because 6 elements. You have X dots, Y dots, Z dots, and you have omega X, omega Y, and omega Z. That is, you have the linear velocity and the angular velocity, and that is related through a Jacobian matrix J multiplied by, you have Q1 dot etc. to Qn dots. If it is an n degree of freedom manipulator, you have n joint angles. So these are the joint angle velocities. Q1 dot to Qn dot is joint angle velocity, and this is the Cartesian velocity, linear velocity, and angular velocity, omega X, omega Y, omega Z. It's angular velocity, linear velocity. This is equal to J multiplied by Q dots, and you can see this is a 6 by 1 vector. This will be a n by 1, and therefore this J will be a matrix with the size given as 6 by n. So this is going to be a 6 by n matrix, because n is the number of joints, 6 velocities, 3 linear velocity and 3 angular velocity, a 6 by n matrix J, and n by 1 vector of joint angles. And this elements of J is given as partial derivative of omega 1 over Q1 etc. So omega 1 Q2, omega 2 Q2, Q1 etc. that given in the table. So that is basically the Jacobian X dot is equal to JQ. So this is the way how you get the differential relationship. So if you know the joint angle velocity, you can find out the Cartesian velocity using the Jacobian matrix. In the same way, if you want to get the desired X dot, if you want to get a particular X dot and you are interested in finding out the theta dots, we can use the inverse of the Jacobian and X dots. J inverse X dot will give you the inverse relationship, which is theta dot is equal to J inverse X dots. That is the inverse of the Jacobian. So if you know the desired velocity in the Cartesian space, if you know the tool velocity needed in the Cartesian space, you can find out what should be the joint angle velocity to achieve the desired Cartesian velocity can be obtained using the inverse of the Jacobian, or theta dot is J inverse X, and J is always a function of the joint angle theta or Q. That is why, because the J will depend on the forward relationship and partial derivative of forward relation with respect to the joint variable. So J will be always a function of theta and actually depends on the present position and position orientation of the manipulator. That is why J will be always a function of theta. So J theta inverse X dot will be the theta dot, that is the inverse Jacobian. Just a simple example to say show how the Jacobian is calculated, then we will go to the more details of the Jacobian. So first, if you have a forward relationship, then the inverse the Jacobian can be calculated directly from the forward relationship. So look at the planar robots, a 1 degree of freedom planar robot, a simple manipulator, simple one link manipulator. So you can get Px is equal to r cos theta and Py is equal to r sin theta, it's a simple relationship. Now we are interested in finding out what is Px dot Py dot as a function of theta dots. So we can take Px dot is equal to Px dot is x dot is equal to r minus r sin theta dots. So if you take Px dot, you will be getting it as Px dot is equal to r sin theta theta dots minus r sin theta theta dots, and Py dot is equal to r cos theta theta dots. And we can write it as a relationship x dot y dot. So Px dot Py dot can be written as x dot y dot is equal to theta dot, because a single degree of freedom, theta dot minus r sin theta r cos theta. So you can see that this is partial derivative of x over theta, this is partial derivative of Py over theta, and this is the Jacobian for this manipulator. So this is a simple way to explain how the relationship is obtained. P x dot y dots equal to minus r sin theta or cos theta theta dots. To take the inverse of this, you can get the theta dot is equal to as a function of x dot y dot also. Take the case of 3R planar manipulator we discussed in the inverse problem. For this case, we have the Px is equal to L1 SC1 plus L2 C12 and Py is equal to L1 S1 plus L2 S12. So for that one, the Jacobian will be, you can again calculate the Jacobian. I am just looking only at the linear part of the velocity because we are not taking the angular velocity here. We will discuss y dot and z dots without looking at the omega x, omega y, omega y for the time being. So this can be obtained by taking the relationship from Px, Py, Pz. So you take Px over theta 1. So if you take the partial derivative of Px over theta 1 and theta 2, theta 3, because we are having 3 angles here. So Px over theta 3, similarly Py over theta 1, Py over theta 3, Pz over theta 1, Pz over theta 3 multiplied by theta 1 dots, theta 2 dots, theta 3 dots will be the relationship, and this is going to be the Jacobian. Now you take the partial derivative of theta 1, Px over theta 1, theta 2, you will be getting the elements of the Jacobian as minus L1 S1 minus L2 S12. So if you take the partial derivative of this, you will be getting the first element as minus L1 S1 minus L1 S12 minus L2 S12 and 0, because it is independent of Px is independent of theta 3, that is why you will be getting this as 0. Similarly, L1 C1 plus L2 C12, L2 C12 0, 0, 0, 0 will be the Jacobian for this manipulator of a planar 3R planar manipulator. So that is the simple way to explain the Jacobian. Of course, we need to get the omega x, omega y, omega z also. So that I will explain with when we talk about something called a manipulator Jacobian, a Jacobian which actually used for getting the force relationship. But in general, by taking the partial derivative of the forward relationship with respect will give you the value of Jacobian. But before going to the statics, let me give you a few insights about the Jacobian. Okay, this is another example for 4-axis Cara manipulator. Again, we'll take only the linear velocities. So it's very straightforward. Get the relationship Px, Py, Pz, and then take the partial derivative, and you will get the Jacobian for the linear part of the velocity, linear velocity. Okay, a few things about Jacobian. When we talk about Jacobian, we always talk about a term called singularity. So in singularity, what actually happens is theta dot is always given as, again, you can have theta inverse x dots, but it is not possible to always have this relationship. Okay, so the joint space velocity theta dot is given as j theta inverse x dot, and one of the problems in this solving joint velocity is the non-existence of inverse. So in some cases you will see that this inverse is not existing because of various reasons. So you are not able to get the j theta inverse. Under such situation, what actually happens is that when j theta is not having an inverse, basically it says that it actually loses its rank, and therefore you don't get the determinant. It actually loses its rank, and at some values of x dot, and whatever may be the, for some values of x dot, you will never be able to get the corresponding values of theta dots, and that situations are known as singularity. That means whatever may be the velocity you want in the Cartesian space, you will not be able to find out the corresponding theta dots to that one, or for any value of theta dot you won't be able to get a desired value of x dot. So this kind of situation is known as singularity in manipulator kinematics. So the Jacobian may not be invertible for all the values of theta. So for because of the theta, j will be having some particular properties, or it loses its rank, and then you won't be able to get the inverse. So at certain points in joint space, Jacobian loses its rank. There is a reduction in number of independent rows and columns, and the points at which the Jacobian loses rank are called the joint space singularities. So joint space singularity is that the point at which, or the joint space configuration at which the Jacobian loses its rank is known as joint space singularity. So normally the Jacobian will be full rank as long as Q is not a joint space singularity. So as long as the manipulator is not in a joint space singularity, it will be always of a full rank. That means you will be able to get the inverse and solve the problem. But sometimes when the manipulator gets into a state where the theta values are such that Jacobian loses its rank, then it will be at singularity. And at this singularity, you will not be able to get the desired movement of the manipulator. And this is normally measured, how close the robot is to a singularity is normally measured using a term called dexterity of the manipulator. So if the dexterity is very low, that means it is close to 0, then basically you are saying that it is actually in singularity. So this is measured using something a determinant of J transpose. So you take the determinant of J transpose, and by looking at this you will be able to tell that the manipulator is very close to a singularity or it is in the singularity space. Okay, for general case the true Jacobian matrix is less than full rank if and only if the M by N matrix J transpose is singular. So if J transpose is singular, determinant is 0, then the dexterity will be 0 and it will be at a singular space. For redundant manipulators, of course you take the J transpose must be used instead of okay, it can be J transpose less number of degrees of freedom, because you need to get a square matrix always. So it will be J transpose J or J transpose can be used. So the determinant of this one, if it is 0, then actually you will be in a singularity or it actually loses its full rank. So the manipulator is joint singularity if and only if the dexterity is 0. So you can actually see how the dexterity changes as theta changes by looking at the determinant of J transpose J, and you will see that when it reaches 0 it is actually singular space, otherwise it is actually away from the singularity, or how close it is to singularity, dexterity value will tell you how close the robot is to the singularity. That singular configuration you won't be able to get the Cartesian space velocity whatever may be the joint space velocity. Whatever you do with the joint space velocity, you won't find any changes in the Cartesian space velocity. That means there is no relationship between x dot and theta dot at that point. And this is actually inside the workspace, and something called the two kind of singularity. One is known as the boundary singularity and the other one is known as the interior or workspace singularity. Boundary singularity is that the robot has already reached its end. So if this is the robot and it has reached its workspace, this is the workspace of the manipulator, and now you are actually reached at this point, the robot is at the tool tip edge, and now you want to get it a particular direction velocity. You want this to have a velocity in this direction, it won't be able to move because it's already reached at singular configuration. It's actually at a singular configuration. It cannot have a velocity in this direction. So whatever you want to have a velocity z dot in this direction, it won't be able to get this velocity because it can actually maximum have a velocity in this direction only. It won't be able to get a velocity, a combination of velocity in this direction you won't be able to get. So this kind of singularity is known as the boundary singularity, where whatever may be the joint angle velocity you provide, you won't be able to get a desired velocity at this point. Take that SCARA manipulator what we discussed earlier. The Jacobian of SCARA is given as minus L1 S1 minus L2 S1 S1 minus etc. So if you take the singular dexterity of this manipulator, dexterity is given as determinant of J transpose. Okay, so J transpose J. So if you do this, you will see that it will become 0 at some condition. So as the dexterity will become 0 when L1 L2 S2 is equal to 0. That means when theta 2 is equal to 0 or 180, this dexterity will become 0. That means when the manipulator is fully stretched, it is fully stretched either at 0 position or 180 degree, it will be always having a dexterity of 0. That means it is at the boundary, and this is known as the boundary singularity of the manipulator. That means it cannot get any further changes in the velocity at that point in any direction because it already reached the boundary of the manipulator. That is the boundary singularity. Interior singularity is the other one which is within the workspace. Within the workspace, sometimes the manipulator joints will align in such a way that whatever you do with the joint angle, you don't see any change in the configuration of the manipulator at the Cartesian space, or you don't see any change in the Cartesian velocity, whatever may be the changes in the join velocity, and that is known as the interior singularity of the manipulator. For example, you look at this manipulator in this configuration. So it has a microbot alpha, and see that Q1 and Q5 are the two joint angles, and the manipulator is aligned in such a way that the positions are Q1 is joint angle first one, then Q2 is minus beta, Q3 is 2 beta minus pi, and Q4 is minus beta, and Q5 is another joint angle. So in this configuration, whatever you do, and again under the condition that A3 is equal to A2 and A4 is equal to 0, then JQ loses full rank along the line Q is equal to Q beta, which represents the interior singularity. Now whatever may be Q1, so Q1 and Q5 in opposite direction, if you rotate, you will see that there is no change in the velocity at the tooltip. The Cartesian velocity does not change even though you actually change the two joint velocities. You change Q1 and Q5, still you won't be able to get any velocity at the tooltip, and such conditions are known as the interior singularity of the robots. Again, the robot actually loses because of the JQ actually loses its rank under that particular configuration, and whatever the theta dot changes, you don't see any x dot change, or whatever if you want a particular x dot, you won't be able to get a theta dot which actually gives you that particular changes in velocity. Okay, for an example, you can do an exercise for a 3-axis planar robot. Show that if A2 is equal to A1, then Q is equal to Q1 pi Q3 is a locus of singularities, and which x's are collinear in this case. It's a exercise for you. Just one more thing about this Jacobian inverse, and then I will stop. See, we discussed that the theta dot is actually J inverse x dots. Another practical difficulty with respect to Jacobian is that given as J inverse x dots, but we know that J is J inverse is defined only for square matrices. So you need to have a square matrix to get the inverse of the matrix, and J need not be a square matrix, because J will be J can be of any size depending on the number of degrees of freedom. It can be 6 by 5, or it can be 6 by 4, or it can be 6 by 7. Only in some cases it will be 6 by 6. So normally, if we have a manipulator which is having 5 degrees of freedom or not equal to 6, we always have a problem of a matrix which is not square, and getting the inverse will be a problem for this kind of matrix, and therefore we cannot really get the inverse of J for practical applications. And this actually leads to problem of getting the theta dot or calculating theta dots. And for this kind of situations, we do something called a generalized inverse. So instead of going for the normal inverse, we do something called a generalized inverse, which actually says that if you can find a matrix which actually satisfy any of the conditions as given in here, if A is an n by n matrix, then an n by m matrix, for any m by n matrix, you can find an n by m matrix which satisfy at least property 1 or 2 of the following list of properties will be considered as a inverse or generalized inverse of A. If A is an m by n, then A inverse will be an n by m matrix if it satisfies the conditions, any one condition, one of the conditions, A is equal to A, Ax is equal to X, Ax transpose is equal to Ax, Xa transpose is equal to Xa. Okay, it's X. So X, if you can find a matrix X of n by m which satisfy any one of these conditions, known as the generalized inverse. And we have something called a pseudo inverse. A pseudo inverse, so we define something called a pseudo inverse, which is normally represented as A plus. Normally inverse is represented as A minus. So a pseudo inverse A plus is defined, which actually satisfies all the 4 conditions, which satisfy all 4 properties what is mentioned here. And if A is a full rank, then A plus is defined as, or A plus is the inverse. So A plus is defined as A transpose inverse if m is greater than n or equal to n, and equal to A inverse, the normal inverse when m is equal to n, and it is A transpose A inverse, it is A transpose A inverse A transpose if M is then N. So for any matrix, any non-square matrix or square matrix, you can always find out a inverse A plus by using this rule. So we don't need to worry about whether J is a square matrix or a non-square matrix. You can always find an inverse, pseudo inverse A plus by using this relationship. If M is greater than N, A transpose inverse. If it is less than N, then A transpose A inverse A transpose. Basically, we are making this a square matrix and then getting the inverse and multiplying with A transpose. Here also this is a square matrix, take the inverse of square matrix and pre-multiply with A transpose, you will get the A plus. So we can be able to always use this pseudo inverse in the manipulator. Otherwise you won't be able to get the inverse. You will always see that the inverse is difficult, and therefore we will be always using pseudo inverse in manipulator kinematics to get the Jacobian. This is an example for pseudo inverse. If A is 1 0 2 1 minus 1 0, the pseudo inverse will be A transpose inverse will be obtained it as 1 over 9 1 4 1 minus 5 1 4 minus 2. So it was a 2 by 3 matrix. Now you are getting a 3 by 2 matrix as the inverse of A, which is the pseudo inverse of A. And this is normally used in control of the robot also. So if you want to control the velocity of the robot in resolved motion rate control, something called resolved motion rate control, we use this Q dots can be calculated from X dot. So you want to have a desired velocity for this manipulator. You want this manipulator to have a desired velocity in this direction with a particular value. So if you know this X dot, Y dot and Z dots, we can actually get this Q dots by using the zero inverse J transpose J inverse J transpose X dots, and or J plus X dots. We will be able to use this theta dot can be obtained as J plus X dots. So if you know X dots, if you want to have a particular velocity control for the manipulator, then we will be able to get the required joint angle velocities to get this X dots, and this is known as the resolved motion rate control in robotics. The robots manipulator robotics, we use something called the resolved motion rate control to control the velocity of the manipulator in a desired way, and then we calculate theta dots using the J inverse manipulator in the Cartesian space. This is basically looking at the same, the Jacobian, but in a different way, the Jacobian, and then use it for getting the static analysis of the manipulator. That's what we are to do. But the principle remains same. Jacobian is a relationship between the velocity and the configuration space and the joint space, and then use it for getting the torque requirement at the joints for a particular force at the tool tip. Fine. So let me stop here. Okay. Thank you very much. Wish you all the best. Thank you.